Chapter 5, Integrals, Section 5.1, Areas and Distances. Let's use rectangles to estimate the area under the parabola y equals x squared from 0 to 1. So first we can draw it. So here's x, here's y, and here's the parabola y equals x squared. Let's use a rectangle. Let's see. If we draw a rectangle like this, from, let's say 1's over here, so I went a little bit too far, but let's say the rectangle was touching at 1, then I could say that the area underneath y equals x squared is definitely smaller than the area of this rectangle, which is 1 times 1. So I know that the area underneath y equals x squared is a number between 0 and 1. But I think we can do a lot better than that. Well, what if instead I tried using 2 rectangles? So I make one over here, where the height of the rectangle is the height of the curve, and I make another one over here. I make them so they both have the same width. That means that the height of this rectangle is 1/4 because it's the y value at 1/2. Because this point is half 1/4. And that means that over here, the y value would have to be 1. So the area of this rectangle is 1/8. The area of this rectangle is 1/2 times 1 is 1/2. And my total area I would estimate would be 1/2 plus 1/8. So 5/8. But I think I could do even better to estimate the area, because notice we still have big chunks of our rectangles that are over the curve, so we're still vastly overestimating our area. So how about we do it with 4 rectangles? So here's a half, here's a 1/4, so here's my first one, second one, third one, and 4th one. So for each of my rectangles, I make it so that the height of the rectangle is the point on the right side. So in this case, the height is the point at the x value of 1/4. This one is the height at 1/2, the height at 3/4, and this one's the height at 1. This should be touching over here. So this is 1, 1. Let's call this estimate R4, because each of my rectangles touches the curve on the right side, and I'm making 4 of them. Let's compute. R4 is the width of the first rectangle, which is 1/4, times the height, which is the height at 1/4, so it's the y value at 1/4. So 1/4 for the width, and then y is 1/4 squared because y is x squared. For my next rectangle, for this one, the width is still 1/4 because I made all of the widths 1/4. But in this case, the height is the y value at the new x value. So it's the height at 1/2, which is 1/2 squared. For the area of my next rectangle, it's going to be 1/4 times 3/4 squared. Then 1/4 times 1 squared for my last rectangle. Altogether, that adds up to 15 over 32, which is 0.46875. Again, this is still an overestimate because of all of these extra pieces of rectangle we have that are sticking outside of the curve. So what if we, instead of doing rectangles on the right side, we did rectangles on the left side? Meaning, I draw this again. So that's y equals x squared. But instead, I'm going to draw my rectangles so that the left side touches the curve. So over here, I draw a rectangle. It has height 0 because the left side is at 0. My next one will have this height at 1/4, and then I draw it out. And then here's my next one with the left side touching at 3/4. Oops. And then my last one. Okay, so this one had the left side at 1/4 touching, left side at 1/2, left side at 3/4, and we end at 1. So let's try to calculate. Oh, by the way, this is the point 1, 1. Notice it lies above the last rectangle this time because it's touching at 3/4 instead. There's a tiny little rectangle over here that has height 0, so I'm not going to even draw it. My first rectangle in that case is that small one of type 0 of height 0, so it's 1/4 times the height 0 squared, because the y value at 0 is 0. Then for this rectangle, my second one, the width is still 1/4, but now the height is 1/4 squared, because it's this y value over here is the height of this rectangle. For my next rectangle, it's going to be 1/4 times 1/2 squared, and then 1/4 times 3/4 squared for my last rectangle. Notice that this rectangle is this rectangle, this one is this one, this one is this one. The only difference is that we swapped this big one on the outside for this small one, which is the same for our sum too. Here's my rectangles of 1/4, my rectangles of 1/2, my rectangles of 3/4. The only difference is these guys in the end, because we started in different places. So this adds up to 7/32, which is what we would expect because it's smaller. Now we have the opposite problem we did before. We have an underestimate because we've got all of this area unaccounted for that's underneath the curve. So this adds up to about 0.21875. Because we have an underestimate and an overestimate for our area, we can now say that the area must be between these two numbers, the actual area underneath the curve. So I could say the area is between 0.21875 and 0.46875. What if we wanted to do it even better? So this was L4. How about we do 8 rectangles? So let's do these guys on the left again. Call this L8. We'll draw our curve and draw 8 little rectangles touching on the left. So that's 2, because remember the first rectangle has height 0. So that's 3, 4, 5, 6, 7, 8. We'll say that's at 1. So here's the point 1, 1. Roughly. Here's 1/8 this time instead of 1/4. I could also get a right estimate. So we'll call this R8. And I'm going to do the rectangles on the right side, so I start off with one over there instead of at 0. So it's 2, 3, 4, 5, 6, 7, 8. And then over here would be the point 1, 1. So I did not draw this very well at all because these two should be like roughly the same height, but you get the general idea, I think. Now we have an overestimate again. Okay, So we have all of these extra little bits, but notice this looks a lot better than over here. Kind of like how this looked better than our first estimate, which was just one entire giant rectangle, or our second, which was 2 rectangles. So it looks like the more rectangles we use, the less we're going to overestimate or underestimate. If we were to calculate these values by adding up the width and height of each of these rectangles, we would get that the area should be between 0.2734375 and 0.3984375. So it looks like we're zeroing in on what the actual area is. If we were to do this again, let's say for 50 rectangles, we would get a lower estimate for 50, a left estimate for 50, and a right estimate for 50. And that would tell us, if we actually did the calculations, that the area has to be between 0.3234000 and 0.3434000. If we did it for 1,000 rectangles, which I'm definitely not going to draw, then we would get 0.3328335 for my left estimate, and 0.3338335 for my right estimate. So it looks like the more and more we do these, that the area is closing in on 0.3333333, which is 1/3. This process should seem very familiar to you. This is just like when we were calculating limits, and we kept getting closer and closer and closer to a specific value. So we keep getting closer and closer to this specific area. Why don't we actually go and find the limit? So for the region in example 1, let's show that the sum of the areas of the upper approximating rectangles approaches 1/3. That is, the limit of Rn is 1/3. By the way, notice that it didn't matter whether we went from the right, the upper areas, or the left, the lower ones. They both approach 1/3. So we'll take this limit of Rn, but we would expect the limit for Ln to also be 1/3. Since we're doing an arbitrary number n of rectangles, our picture gets a little bit different. Now we have just tons of rectangles flying around. Let's see how well I can draw this. So we're going above. Oh, not very well apparently. We're going to the right. Tons of tiny little rectangles. So let's say this is one. Let's stop over here. This is the point 1, 1. I don't know how many rectangles it is, but they're all the same width, and they should start at 1/n. So remember, this is still y equals x squared. There should be tons and tons of these little rectangles because we're going to take n to approach infinity. So they're all overestimating a little bit, and they all have width 1/n. So let's get Rn, the right estimate. Well, each rectangle has a width of 1/n, so the first one has width 1/n, and its height is the y value at 1/n, so that's 1/n squared. The second one also has width 1/n, but the height of the rectangle in this case is the second x value, right? It's going to be the y value at that second x value, so it's the y value at 2/n. So it's 2/n squared. The next one will be, again, with 1/n, but then the height is the y value at 3/n, so it's 3/n squared. And we keep doing this, and so on, until we get to the last rectangle over here. So that's with 1/n. And then notice what the height is going to be. Well, if we have n rectangles, we go from 1, 2, 3, 4, and so on. We'll go until we get to the last rectangle, which would be n. So it should be n/n for the last one, which makes sense because the last one's at 1. So we have n over n squared. What we can do now is factor out 1 over n because it's in every single one of these. We get 1 over n times, well, we can also factor out 1 over n squared, because when you square the top and bottom over here, you get a 1 over n squared. Over here, you get 2 squared over n squared, 3 squared over n squared, n squared over n squared. So there's 1 over n squared in all of them also. We factor that out too. Left inside is the 1 squared, 2 squared, 3 squared, and so on, all the way to n squared. So let's multiply these. We have 1 over n cubed times the sum of all of these squares. There's a formula for the sum of the first n squares. Like if I want to sum 10 squares, I don't have to actually add up those individual 10 numbers squared. I can just plug them into a formula. And that formula says that it's n times n plus 1 times 2n plus 1 over 6 when you add it up, which ends up becoming n plus 1 times 2n plus 1 over 6n squared, because we cancel out 1n on top and bottom. So you may be saying, okay, well, you kind of pulled a fast one over here, because you took this mess and you replaced it with this formula, but we've never even talked about this formula. So how about we prove it? Let's do proof by induction. And that'll be for this, that this happens to equal the thing that we replaced it with. So we need to start with a base case if we're doing induction. So we have to prove that the formula works for 1. So we need to test that 1 squared actually equals 1 times 1 plus 1 times 2 times 1 plus 1 over 6. Which it does. This is 2, then this is 3. 2 times 3 over 6 is definitely 1. All I did was I plugged in 1 for n, just to check that the formula works for 1, and it does. So now we need to check our inductive step. What we have to do now is assume that it's true for some number k. So we'll assume our formula works for 1 squared plus 2 squared plus 3 squared all the way up to some number k squared. We're assuming that this will in fact equal k times k plus 1 times 2k plus 1 over 6. What we have to now prove is that if I go to k plus 1, if I go one more k after, and I square it and add it up to the rest of them, that it actually equals the formula with k plus 1 plugged in instead of k. So let's do that. Well, if this is true, then let's look at 1 squared plus 2 squared plus 3 squared all the way up to one more, k plus 1 squared. Okay, so there's still a k squared in here. So I could write this as 1 squared plus 2 squared plus 3 squared all the way up to k squared plus k plus 1 squared. All I did was show the k squared that I didn't show over there. That way I can write this separately as the sum I had before. But we just said that we're assuming that it's true for that sum. So I can replace this with the actual sum that we're assuming is true. So I can replace it with k times k plus 1 times 2k plus 1 over 6. and I still have the plus k plus 1 squared. Notice I could not just replace the entire thing with this because we only assumed it was true up until k. The whole point is that we're trying to prove that it works even if we go past k. So now I have, let's see, I can factor out, I've got a k plus 1 here and I've got a k plus 1 there. So let's factor out k plus 1. Left inside will be k times 2k plus 1 plus another k plus 1. But how about we find a common denominator, multiply the top and bottom of this guy by 6, and we get 6 times k plus 1. And then we can combine the two to make them both over 6. So we keep our k plus 1 on the outside. We distribute and combine like terms on the top, and we get 2k squared plus 7k plus 6 over 6. And this is equal to k plus 1 times k plus 2 times 2k plus 3 over 6. We just factor it. But hang on, this is perfect, because remember our formula was k times k plus 1 times 2k plus 1. Now we have k plus 1 times k plus 2, but that's the same as k plus 1 plus 1. So this becomes k plus 1 plus 1, and the last one we could write as 2 times k plus 1 plus 1. So that is exactly what we wanted to prove, because that's just the formula with k plus 1 plugged in instead of k. So by induction, since we proved that our base case works with 1, and we proved that assuming that it works for k leads to it working for k plus 1, now we have proven the formula. So we return to what we wanted to show, which was that the limit is 1/3. So far we've managed to come up with a nice kind of closed formula for our upper sum, our right sum. We did a little bit of work to actually prove that the sum of the first n squared numbers actually is this formula. In general, what we're going to do from now on is we're not going to prove these formulas. We're just going to take them for granted. But I think it's good to do at least, one nice induction proof. So how about we close this off a little bit. And this was our nice proof by induction. Let's take the limit now. So the limit of Rn is the limit as we computed and proved. It's n plus 1 times 2n plus 1 over 6n squared. Well, the limit of a product is the product of the limits. So that means it's the limit of 1/6 times n plus 1 over n times 2n plus 1 over n, which is the limit of 1/6 times 1 plus 1 over n. We just split the two terms on top, and we split the two terms on the other in the other factor. So we get 2 plus 1 over n. Well, now limit of 1/6 is 1/6. Limit of 1 plus 1 over n is 1 plus 0, so that's 1. And similarly, we get 2 plus 0, so that's 2. So this limit does equal 1/3. Again, we could have proven this for Ln instead of Rn, but we just chose to do Rn. Let's do another definition now. I think it makes sense to define the area of a region S underneath the graph as the limit of the areas of a bunch of rectangles. We could have defined this using Ln, but seeing that Ln and Rn both seem to approach the same value whether we go above or below, we can just arbitrarily pick Rn. Notice that even though there is an overestimate sometimes when you have Rn. As you get more and more and more rectangles, the little bits that you are over the curve get smaller and smaller and smaller. When you go towards infinity, those little bits become negligible, and you pretty much approximate exactly the area of the curve, so you get the exact area. So what we're doing is we're using sigma notation to write this a little bit smaller over here, more compactly actually. Sigma notation says that you add up all of these terms from the bottom, so from I equals 1 all the way up to n. So what we're saying is we take each of the y values for each of the rectangles, we multiply by the width. Notice the width is the same for every rectangle, it's just the change in the x. And once we have all of these areas added up, then we take the limit of how many rectangles we're adding up. So we're trying to go like, a million rectangles, 2 million, 3 million, all the way up to infinity. And that'll be our area underneath the curve. Compactly, it's the limit of this sum of all of these y values, that's the height of each rectangle, times all of the widths of each rectangle. Okay, so these numbers xi star in the ith subinterval over here are called sample points. So in this case, x1, x2, xn, those are our sample points. We're choosing those sample points on the right side, so those are all chosen from the right side of the interval. We didn't have to do that though. We could have chosen on the left side, in which case this would have been x0, which is a if we're starting at a. And then this would be x1, all the way up to xn minus 1. But it depends on, what you choose. In this case, the xn is actually b, the last point in the interval, because we're going on the right. This means that the width, delta x, we could write as the last point in the interval, the last x value in the interval, minus the first, that entire difference, b minus a, and we just divide by how many rectangles we're using, n. This will tell you the width for every single rectangle. So if I have, let's say, from 0 to 1 like we did before, and I want to do 2 rectangles, that would be 1 minus 0 over 2, so each rectangle would have a width of 1/2. If I were doing rectangles, it makes sense, it'd be 1 minus 0 over 10, each one would have a width of 1/10. So in general, it'd be b minus a over n for the width. However, we don't have to choose these sample points at the right or at the left. We could choose them somewhere in between, like over here, or right in the middle, like over here, or a little bit to the right over here. These sample points that we plug in for the height of each rectangle can be chosen anywhere. We didn't have to make the rectangles perfectly align on the left like we did, or on the right like we did. Instead, we could just draw the rectangles however high we want, by picking any x value inside the intervals to plug in. So when we choose the sample points to be on the right, that's when we get Rn. When we choose them to be on the left, that's when we get Ln. But if we choose them to be in the middle, for example, we would get something like Mn for a midpoint. We use the star to denote that it's a sample point chosen anywhere inside of there. When we make the choice, sometimes we lose the star and we get just like an exact point at the end of the interval. But in general, xi star could be anywhere inside of the interval. Let A be the area of the region that lies under the graph of f of x equals e to the minus x between 0 and x equals 2. Using right endpoints, let's find an expression for A as a limit. Do not evaluate the limit. Okay, so let's do A equals 0, B equals 2. So that means the width of all of our rectangles will equal 2 minus 0 over n, which is 2 over n. If it was from 0 to 1, it would be 1 over n, so it makes sense that from 0 to 2 would be 2 over n. We're going to get a right estimate now. So Rn, which is equal to f of x1 delta x, because our sample point is chosen to be x1. For our first sample point, it's always chosen to be on the right. And then f of x2 delta x, and so on until we get to the last one, f of xn delta x. So in this case, f is e to the minus x. So we get e to the minus x1 delta x plus e to the minus x2 delta x, and so on. Could have factored out these delta x's, but it's okay, we'll leave them in for now. Oops, that's supposed to be delta x. So then, let's see, we need to now plug in what x1 is. Well, the first x value will be 2 over n because we're starting at 0. Then the next x value would be 4 over n, and then 6 over n, and so on, because each one is 2 over n far from the previous one. So that means that we're looking at e to the minus 2 over n for x1, and then the width is 2 over n, plus e to the minus 4 over n times 2 over n, plus e to the minus 6 over n, and so on, until we get to the last one, which, let's see, if we're looking at all of these things all the way to the last one, before the last one was at n, but now each time they have a width of 2 over n, so the last one should be at 2n. So this should be e to the minus 2n over n. Notice that also matches with the pattern here. 1 gave you 2, 2 gave you 4, n should give you 2n. Oh, almost forgot my 2 over n for my width. So I think we can say that the area, which is the limit of Rn, is the limit of this mess. We could factor out the 2 over n and just be left with e to the minus 2 over n plus e to the minus 4 over n plus e to the minus 6 over n, why not, and so on, until we get to e to the minus 2n over n, which, by the way, cancels and gives you 2, which is exactly what we want. But it's good to have the n over n notation because it shows us what we can plug in to write this, if we wanted to, as sigma notation. In sigma notation, this can be written as the limit of 2 over n times this entire sum. So we use sigma for sum. We're going to start at 1 because we started at x1. So we're starting at I equals 1 to n. And instead of putting in 1, 2, 3, 4, 4, whatever, we're going to just put in I. So it'll be e to the minus 2i over n, because that's what the pattern is 2 times whatever number it is. This is a very hard sum to evaluate directly. But if you were to plug this into a computer algebra system, you can get it pretty quickly. Instead of trying to evaluate the limit, though, we're going to try to approximate it instead. Let's estimate the area by taking the sample points to be midpoints and using 4 subintervals and then 10 subintervals. So this means we're going to do a 4 rectangle estimate and then a 10 rectangle estimate. Let's see if we can try drawing what this thing is going to be. So let's say here's, look at that a little bit better. Let's say here is y equals e to the minus x, and then here's x and y. Here's 1. I want to draw 4 rectangles. However, I'm taking my sample points to be midpoints. So I'm not going to draw the rectangles touching on the left or the right. I'm going to draw them touching in the middle. So something like this. That will be 1 rectangle touching in the middle. And then, let's see, that'll be a 2nd rectangle touching in the middle. And then it becomes a little bit harder at this point. third, and I need a fourth. Let's see if I can do it. These are supposed to be the same width, so I don't like that so much. Let's see if I can draw this a little more. Okay, that'll do. Notice that the rectangles are both a little bit of an underestimate and a little bit of an overestimate. It's hard to see from the picture whether our midpoint in general will be an over or underestimate because these areas are not equal to each other. One of them should be more than the other one. But how about we just say this is x1 star, this is x2 star, this is x3 star, and over here the last midpoint is x4 star. And remember, it goes from 0 to 2. So over here, if I were to look at this point, this is x1, my right sample point. Over here, this is x2, x3, and x4. Sometimes we choose our endpoints x1, x2, x3, x4 to be equal to the sample points, but in this case we didn't. We moved the sample point to the left a little bit, halfway, so that it would be at the midpoint. Sometimes we choose them to be over here. This would be like x0 or the a value at 0. We can choose that to be the first, or choose the left signs to be the sample points, in which case the sample points would all move to the left. So with n equals 4, let's see what the width is going to be. Delta x. Well, it doesn't matter if I choose my sample point in the middle or on the right side for the width. The rectangles will still all have the same width. It just changes the height of the rectangle. It just changes where I put it. But it doesn't change how many of them, and it doesn't change how wide they are. So my width is still how long this is, and how wide each rectangle is, and that's still the difference in those two x values. So if we think of it as b minus a over n, that's 2 minus 0 over 4, so that's a half. That also makes sense because over here is 1, and then over here is a half. So from here is 0 to a half, then half to 1, then 1 to 1 and a half, 1 and a half to 2. So each rectangle has width of a half. We can even write each interval out explicitly. The first one goes from 0 to a half. The second one goes from half to 1. And the third one goes from 1 to 1 and a half. And the last one goes from 1 and a half to 2. So let's look at what the sample points become. Not so good at these stars. So x1 star is in between 0 and 1/2. It's halfway in between, so that means it's 0.25. It's in the middle of this interval. The next one's in the middle of this interval, so it's 0.75. Then 1.25. And then 1.75. So now we can write out M4, our estimate with 4 midpoint rectangles. In sigma notation, that's going to be the sum starting at 1 and going up until 4 of f of xi star times delta x. So our first xi star is 0.25, so that's f of 0.25 times delta x plus f of 0.75 times delta x plus f of 1.25 times delta x plus f of 1.75 times delta x. Plugging that into our function, remember it's e to the minus x, so it's e to the minus 0.25 times our width, delta x is 0.5, plus e to the minus 0.75 times 0.5 plus e to the minus 1.25 times 0.5, and lastly e to the minus 1.75 times 0.5. We can factor out that 0.5, so we factor out a half, and we write out all these e's again for basically no reason, but it's good to show every step, and that way we can see that we're actually not messing up the entire thing, especially with so many numbers going on over here. If we use a calculator, we get that this is approximately 0.8557. So that means that our area is approximately 0.8557. To get the exact area, we would have had to take a limit here. Let's do this now for 10 subintervals, so 10 rectangles, which I'm not going to draw. I think you guys can use your imagination, hopefully. So with n equals 10, now delta x is 2 minus 0 over 10, so it's 0.2. Each rectangle has a width of 0.2. That means that my first interval goes from 0 to 0.2. My second goes from 0.2 to 0.4, and so on until I get to the 10th subinterval, which goes from 1.8 to 2. I now need to take my sample points to be the midpoint of each of these guys. So x1 star is in between 0 and 0.2, so it's 0.1. And x2 star is therefore 0.3. x3 star is 0.5. And we keep on taking all of these midpoints until we get to x10 star, which is 1.9, in between 1.8 and 2. So now we can approximate our area using our midpoint estimate for 10 subintervals. So that's f of 0.1 times delta x plus f of 0.3 times delta x plus f of 0.5 times delta x, and so on, until we get to f of 1.9 times delta x. Plugging in, we see that this is 0.2. We can factor out, that's delta x, times e to the minus 0.1 plus e to the minus 0.3 plus e to the minus 0.5, and so on until we get to e to the minus 1.9. Using a calculator, we see that that's about 0.8632. We would expect that to be a better estimate for the area than our previous one, but the previous one actually wasn't too bad either, and it saved us from having to do 10 of these things, so I don't know. Suppose the odometer on a car is broken. Let's estimate the distance driven in feet over a 30-second time interval by using the speedometer readings taken every 5 seconds and recorded in the following table. Well, our table says time is in seconds and velocity is in miles per hour, so this would be better if we converted it. Let's leave time in seconds, but let's make velocity into feet per second. That way we have seconds over seconds, so we'll have consistent units. And we need to change from miles to feet, because if we change from hours to seconds, then our units would just, our numbers wouldn't be aligned at all properly. They'd be just way too small. So we'll go 0, 5, 10, 15, 20, 25, 30, and our velocities when we convert become 25, 31, 35, 43, 47, 45, and 41. let's look at this from, let's say t equals 0 to t equals 5. We're going to assume that from 0 to 5, the velocity doesn't change much. It just goes from 25 to 31. So we'll calculate the distance traveled, assuming a constant velocity. How about you assume that it'll just stay at 25 the entire time? So we'll choose the left. So that'll be 25 feet per second times 5 seconds. So that means 125 feet were traveled. Rate times time equals distance. If we do the exact same thing for, let's say, t equals 5 to t equals 10, then we have to make another assumption about the velocity the entire time. So let's just assume it stays 31 the whole time until it gets to 10. So that would be 31 feet per second times, again, 5 seconds. And we would get 155 feet. We can keep doing this process. So 25 times 5 for my first distance traveled estimate, plus 31 times 5 for my second one, plus 35 times 5, plus 43 times 5, plus 47 times 5. So let's see, I need one more. 43, 45. Oh, oops, I skipped 47. 47 times 5 plus 45 times 5. Okay, let's make sure this is right. This goes from 0 to 5. This goes from 5 to 10. This goes 10, 15, 15 to 20, 20 to 25, and from 25 to 30. Notice we're not going to use the 41 because we already used 45 as the estimate from 25 to 30. This ends up becoming 1130 feet added up all together. So if we're to draw what the situation looks like, it looks something like this. Here's velocity, here's time. We're going, let's see, how about 10 over here, 20 over here, and 30 over here. So then we can go, here's 0, here's 20, here's 30, and here's 40. So we start at 25, so we start over here. Then we go to, after 5 seconds, it's 31. So let's say somewhere over here, and so on. We just make a nice little dot plot of our data. Something like that. So then this curve is our velocity curve. What we're doing is we're estimating that the velocity stays constant on each of these 6 subintervals. So that means that we're saying that the velocity stays constant over here, which is the same as drawing a rectangle over there. On the left side, our velocity stays constant over here, and over here, and hopefully your rectangles look better than mine. This one didn't come out so good. So you'll notice for part of the curve it's an underestimate, and for part of the curve it's an overestimate, and we chose all of our values on the left. So you could think of it as choosing our sample points for what we evaluate with the velocity to be on the left side. Notice that didn't change our delta x, basically, our change in time. In this case, it's delta t. Okay, let's say we had used velocity at the end of each time period instead. Let's say that we drew right rectangles, so that would have looked like this. And then going down, like, oops, would have been like that. So it would have been an underestimate at the end and an overestimate at the beginning. Then we would have gotten 31 times 5 for the first one because we would have assumed on the right side. So we would have used all of these numbers and would have skipped the first one, just like we skipped the last one for when we did on the left. So our right estimate would look like this. 31 times 5, 35 times 5, 43 times 5. All of our values are pretty much the same except for the first and last one. 45 times 5 and 41 times 5. That ends up adding up to 1210 feet. So we could say that this is basically L6 and this is R6. So we've managed to estimate the distance driven even though we had no odometer to measure distance just by using velocity.